All right. Hey class, Adam Ward here. I want to work through example 5.6 out of your textbook in Minds. And the reason we're going through this example goes with three real topics that we've covered thus far. We're going to practice conservation of mass. This ultimately is an end member mixing problem, and we'll think about control volumes and how we might draw them. So here's what problem 5.6 out of the textbook looks like. The example here is a reverse osmosis water treatment plant. That's what's labeled in the box, ROWTP. And while there's a lot of information about RO, let's start to unpack this problem. So we're told that this is a 3.785 megaliter per day treatment plant. So I want to recognize that that's a volumetric discharge Q, and what I've gone ahead and done is in orange just labeled where that flow represents. And I've already now assumed that water into the treatment plant and out are going to be equal to one another. We're told that we start with groundwater that contains 150 milligrams per liter. This is not something you would know at this point in the class, but what comes out of a treatment plant like this has a concentration of 0 hardness. That's what they mean in the problem when it says the product or permeate. And ultimately, the way this plant works is that you are going to make this perfectly pure water in your reverse osmosis plant. Then you're going to take some water that hasn't been treated and bypasses the plant, and that's the blue arrow in the diagram. And the idea is at the end of the day, you want to mix those two together and end up with a concentration of 50 milligrams per liter. Okay. The key question here is how much untreated water are you going to blend in? In other words, find this bypass value. So right here, what I'd like for you to do is hit pause, take a moment, and think about this yourself before you watch me solve it. All right, welcome back everybody. You've got an answer in mind. Now let's work through mine. Here's our same diagram on the right. And the key thing here is that if we're going to solve for this bypass flow, we need it in an equation. In other words, if you drew your control volume around the entirety of the problem, so let me do that real quick in yellow. If I drew a control volume that looked like this, everything about Q bypass is internal to the control volume, which means it won't show up in any equation and we won't have the ability to solve this problem. So we need to think through how exactly are we going to set up a system of equations to achieve what we're trying to do here. And so to that end, I'm going to go ahead and use this control volume drawn in red. I've selected it because it has that bypass flow coming into it, and it's also got a lot of information that we know. So for my control volume, first I'll analyze it with conservation of mass of water. And so what I've written out in purple here is that the density of water, mass per unit volume, multiplied by the volumetric flow rate, volume per time, for each of the three arrows shown in purple. Right? So RO being what came from reverse osmosis, B being bypass, and out being what flows out of my control volume. And so each of those terms has units of mass per time, and that's appropriate when we're working on a mass balance and thinking about fluxes. And as we did during our lecture, we recognize that the density of water is not changing through any of there, so we can divide all the terms by density, and what we find is that the total volumetric flow rates in equal the volumetric flow rate out. Now, similarly, we can write an equation for conservation of mass of our constituent, in this case hardness, and each of those terms can be expressed as a volumetric flow rate Q multiplied by a concentration C. And with these two equations written, now I want to just take stock of what we know. And so in gray, you can see that I've gone through for values that I know, I've put a check mark above them. So these are values that are given that we had mapped out on the previous slide. For values that I don't know, I've gone ahead and used a question mark. And what I find is that we have two equations, one in purple and one in green. We have two unknowns. And so this is a solvable problem. At this point, we have at least as many equations as we have unknowns. If we would have had two equations and three unknowns, I would be very sad. What I would realize is, hey, my strategy is incomplete. I need to bring more information to bear on this problem. Maybe I need to draw a second control volume somewhere to be able to generate some additional mass balance equations. But in this case, the problem is solvable. There's a happy, smiley atom over there in gray, and we can proceed. So with our strategy in place, having checked that we think it's a solvable problem, now it's time to do some math. So I'm going to take equation 2 in green, and I'm going to start to put numbers in. So working from left to right, Q from the RO plant is 3.785 megaliters per day. That's QRO. And we're multiplying that by the concentration that comes out of the plant, which is 0. Plus, so now the second term in the equation, the bypass flow, we don't know, so QB. But we do know that bypass flow is at 150 milligrams per liter. Then on the right-hand side, you'll notice what I've done in purple is I've gone ahead and I've substituted in that definition from conservation of mass of water. So instead of Q out, which I don't know, I'm recognizing that Q out is equal to 3.785 megaliters per day, the Q from the RO, plus that unknown bypass flow. But we do know that we want to achieve 50 milligrams per liter as the output. And so by the power of algebra, you should be able to go through and solve this to find that the bypass flow should be about 1.9 megaliters per day. Okay. So hopefully working through this has given you some examples or some practice with conservation of mass, with end member mixing, and just again practicing that problem solving strategy of unpacking the problem to figure out what do I have, what do I need, what's my strategy, is it solvable, and only by the time that I've done that do I start worrying about the math. And that will always be my recommendation to you is let's get a strategy in place before we just blindly start converting units or trying to come up with some equation that's solvable. That's the most efficient way to get through a problem, and it's what I would love for you to work on in this class. All right, thanks for sticking with me, everybody. I will see you all in lecture.